So we're going to walk through several different acid-base titration scenarios, and starting with the simple one, which is just titrating a strong base with a strong acid. And so that looks like just adding pure protons to pure hydroxide groups to make water. And if you think about this, this is the reverse of the dissociation of water. Right? If the dissociation of water were H2O breaks apart into H plus hydroxide, we know that that's governed by the equilibrium constant Kw. So if you simply flip the reaction around, then we are now operating based on 1 over Kw. So 1 over 10 to the minus 14 is equal to 10 to the 14. What does that tell you about the extent of this reaction? Well, it lies massively towards the products, which all titrations will do. That's the whole point of titrations, is we design the reaction to run to completion. Here, this completion is massive, 10 to the 14. So the protons in the hydroxide will instantly react. So a strong base being titrated with a strong acid, the titration curve is going to look something like this. So remember, to extract or to experimentally generate a titration curve like this, you need a pH meter instead of simply a color indicator, a dye indicator. So here you'd have a beaker of your strong base, your original solution, you'd have a pH meter inserted, and then you'd be titrating with a burette that were full of some known concentration of strong acid. Typically you know that to at least 4 significant digits, what we call a standardized strong acid. So just as an aside, for real titrations, quantitative titrations, you don't just use any strong acid that you make up. Typically you have a strong acid and then you have another strong base that you know with high precision and high accuracy exactly its concentration that you measured usually by mass. So because we can measure things by mass in 4 or 5 sig figs, you probably weigh out some KOH, you would add a known volume of water, you get a very accurate concentration of base, use that to standardize your strong acid, and you probably have people do that 10 times, so you get some fairly good statistics on this. Then that strong acid becomes your titrant, and you know that to 4 sig figs with minimum error. Then you hold on to that for as long as you need to, and you use that to titrate whatever your strong base unknowns are. That's the experimental process there. So the titration curve looks a lot like this. Always. So we start at high pH because we're starting with a base. We add additions of protons here. And we really have just sort of 2 regions of the curve, which make it really easy. We have either excess base or we have excess protons. The equivalence point, remember, the equivalence point, and I defined this in earlier videos, the equivalence point is the theoretical point where the moles of the base in this case are equal to the moles of the protons. That's theoretical. Right? If we knew the concentration of each of those, that would be the theoretical point at which they're equal. We call that the equivalence point. The end point is the same thing, except it's the experimental version of that, which typically has some error associated with it because it's based on our perception as humans. It's not a theoretical value, it's our empirical value. The equivalence point will always occur at a pH of 7, and we'll talk about why that is, and that simply is just because when you add exactly the right number of moles of acid to completely neutralize all of the moles of base in there, at that point in time in solution what you have is pure water. What is pure water? Well, pure water could then participate in its own equilibrium, dissociate into protons and hydroxide ions via Kw, which sets the proton concentration equal to hydroxide concentration at that point, which is equal to 10 to the minus 7 molar. Negative log of that gives us a pH of 7. And so by definition, for strong acid, strong base titrations at the equivalence point where you have exactly equal amounts of both acid and base, which is the definition of equivalence, and you have pure water, then the pH at that equivalence point will always be 7. That's what you see here. What else do we see? Well, we see a rapid change in pH around that point because you now no longer have excess of hydroxide and you're sort of swinging from excesses, and you don't have a buffer because we don't have a weak acid and its conjugate base. We simply have strong base and strong acid. So we're going from pure base to pure acid and nowhere in between. So we have this really sort of asymptotic relationship here where the equivalence point occurs. The other point that we identify, which theoretically is the same as the equivalence point, is the inflection point of this curve. The inflection point here is where the slope becomes highest. And you can imagine if we were to take the derivative of this curve, it would help reveal that. Let me sort of show you. So I'm just going to overlay this in green, what the derivative would look like. So remember, the derivative is just the change in pH over the change in volume, which is the same as, rise over run. So it's the slope. It's the slope of the black line. So what we could do is make another plot where we have the slope, the dpH, the change in pH over change in volume on the y-axis. So we'll just make this the green axis here. And then we'll plot on the x-axis the same. We'll keep it volume. So all we're doing is changing pH to dpH dV. What would that look like? Well, if this axis is the slope, at early points on this curve, on the black curve, the slope is fairly small. It's almost flat right at the beginning, and then it starts to grow faster and faster and faster, and then it gets to a maximum where the inflection is, and then it goes away. And so what we'd expect is essentially 0, and then this slow increase, and then a rapid increase right where the inflection occurs. That's where the slope is highest, and then it's symmetrical about that, and so we start to see the slope, or dpdh, go back down. So that would be the slope, dpdh. And so you can imagine it can be kind of difficult from the black line to actually figure out exactly where the inflection point is, but if you have that data, pH versus volume, then simply taking the derivative of that curve is fairly easy. And I'll show you how to do that in a different video in Excel. We don't need MATLAB or anything, although we could use that. That'd be nice too. That works. But even then, this becomes a little bit tricky because depending on how sharp your equivalence point is, how well you collected your data, because remember, this data is not continuous here, right? As an experimentalist, these are all individual points that you are reading out off of your pH meter. And maybe you're reading out, with little bits of volume addition, and you're keeping your volume addition spaced equally, and then all of a sudden you keep spacing it equally right here, and between this point here and this point here, it's the same dV, it's the same volume change, but you just spanned like 8 orders of magnitude, right? And so it's really important when you're collecting data where you have large inflections like this, that maybe at the beginning you space your volumes fairly large because those data aren't important, but if you're computing the derivative, now you've only got 2 points spanning this entire range. That's going to create a really rounded derivative here, so it's not going to be that easy to denote. And so you would try to space your points really, really close as you start to see larger swings in pH. So you have a higher concentration or a higher density of data points right around the inflection point. That's going to give you the best data. So, it can be a little tricky to do this with just simply doing the first derivative. So what can be better, and what's stated straight on here, is that we can actually take the second derivative of this, which would be this. And what would the second derivative? Really, it's looking at the slope of the green line, right? So let me move this over so that we have a little bit more room. So to do that, all we would do is just compute the second derivative and then plot that directly on top, which would be second derivative pH dV squared. Then we would still plot the volume on our x-axis. So if we were to think about the slope of the green curve, how that's changing, well, you see it sort of going in an increasing direction, and then it gets rapid, so it increases quite rapidly or exponentially there, but then it inverts in sign rapidly right at the inflection. So I could trace that in blue here. What we'd see is sort of this increase, and then we'd see a rapid increase until we got to exactly that point, and then we see a sign change because it goes negative, which means we'd end up having this thing drop all the way down like this, and then trace back like this. So the blue line would be our second derivative, and the inflection point then could be defined even easier. We don't have to have that rounded sort of first derivative. We would be able to identify it simply because it would be the point where that equals 0, or it crosses that axis, and that's what's being stated here. And so we can set that line to 0 and solve for that value where it crosses the x-intercept, and that will give us the most accurate indication of the experimental inflection point. And this is often done with titrations, especially if you're doing this for research, because rather than sort of simply looking at the line right here and saying, yeah, that seems like, well, it seems like that's where the inflection point is, like on that line. It's roughly right there. In fact, what we'd rather do is take the second derivative of pH with respect to volume, plot that versus volume, and then extract the intercept with x. That would give us the closest accurate value that we can get. And this is true with any type of titration, not just acids and bases. So if you do redox titrations or potentiometric titrations, the second derivative is always going to give you the best data. And again, I'll show you how to do this in Excel. It's pretty easy so we'll do this with a quick example, and then we're going to look at the sort of three regions of the titration curve that we have here. The region where we have XSOH, the region at equivalence, and then the region in excess protons, so that we feel comfortable calculating the pH or the concentration of any species at any one of those sort of general regions. So what we've got is 50 milliliters of 0.02 molar KOH, the base, and we're titrating that with 0.1 molar HBr as our titrant. So I have a little mini picture here. I always like to draw pictures of any titration that I'm doing, or really any reaction that I'm doing, just to give me perspective for how I should be thinking about that. So the three regions we're going to talk about are pre-equivalence, which is one I have labeled over here, equivalence, which is right at the inflection point, and then post-equivalence, which is the section 3 here. So let's just pretend that we added 3 mils of HBr to our original base. How do you know that's pre-equivalence? Well, you'll know once we talk about the equivalence point. We know that these are one-to-one reactions, so we could pretty quickly figure out how many milliliters of HBr is required to neutralize all the KOH. That number of milliliters will be the volume at inflection, so any volume below that will be this region 1 pre-equivalence. So I'm just telling you 3 is that, but we'll see pretty shortly when we talk about part 2. So how do we do this? Well, we should probably think about how many moles of protons are being added when 3 mils of 0.1 molar HBr are added to the system. So I just grabbed the concentration of HBr, which is given to us in the problem. That's 0.1 moles per liter. I write that out as 0.1 moles H plus per 1,000 mils, just to skip that conversion factor from mils to liters or liters to mils, and then multiply by 3 mils, being the amount added. That gives us 0.300 times 10 to the minus 3 moles of H plus, or HBr, that are added to the original base solution. So second step is just to figure out how many moles of base we started with, because we now know how many moles of acid we are adding. So I just take the 0.02 molar, so that's moles per 1,000 mils, multiply that by the 50 mils, the volume that we had. It gives us 1.00 times 10 to the minus 3 moles of hydroxide initially. So we know this reaction is 1-to-1, so we could just simply subtract these two things if that's convenient and fast, or you could just be you could be a little bit more comprehensive and write this out as an IE table really quickly. And so we have the initial amounts of each of these things that are being added before we allow them to proceed to equilibrium. At equilibrium, we know that all of the protons that are added to the system, which is less than the hydroxide, are going to be destroyed, and they are going to be subtracted from the hydroxide to create water. So that's going to leave us with 0 in the protons, and this is going to be 1.0 minus 0.3, which will give us 0.700 times 10 to the minus 3 as the moles of hydroxide at that point in the titration. So once we know that, then all we need to do to figure out the concentration of the hydroxide at that point, because we still have excess hydroxide, that's the region we're in, would be to take the 0.700 times 10 to the minus 3, which would be 0.7 millimolar, divided by the total volume in that situation, which in this case is going to be the original 50 plus the 3, which would be 53 mils, and then I'll convert that 1,000 mils per liter. Solve this, that gives us a value of 0.0132 molar hydroxide. I'm keeping probably too many digits here just because I'm constrained by the 3.0 mils. So actually this should be probably 0.013, but that's okay. It's not important right now. So we're trying to get to the pH at this point after the addition of 3, which would be right here. So this is the concentration of hydroxide. So you can do this two different ways. You can either take the negative log of this and get pOH and then subtract that from 14 to get pH, or you can do that in the non-log space, which would mean to take the value, since we know that proton concentration times hydroxide concentration equals 10 to the minus 14, we could divide that value into 10 to the minus 14. So get rid of that. That becomes divided by 0.0132. That's going to be equal to proton concentration, and then take the negative log of that. Either way works. Just be careful as you're going from regular space to log space that you're being careful about those sig figs. So doing that, that gives us a pH of 12.12, keeping 2 sig figs there, which I think is what we needed because we're constrained there. So that's 12.12, which is pretty consistent with this, this computed curve right there. So I'm going to show you an alternative approach to doing the same computation. This is the approach that your book will take and other books will take, and it's just a little bit faster than doing dimensional analysis at each step and using a little bit more of our intuition. So in order to do this, the alternative approach, actually the first step we need to do is just figure out what's the volume at equivalence. So how do we figure out this point? Here you can see it's 10 mils. We call that V sub E for the volume at equivalence. Sometimes people write that V sub EQ for the volume at equivalence. How do we figure that out? Well, that's just we can do that dimensionally, or just an M1V1 reaction, because we know this is a 1-to-1 reaction. So we had an original concentration of the base of 0.0200 molar, and we had an original volume of 50 mils. And then we're titrating that with a base, or an acid at 0.100 molar HBr, and the volume that's used to completely titrate all of that would be X, and in this case X would also be the VE. So we could compute that. If we solve this, this gives us 10.00 mils, which is our volume at equivalence. So what we know is that any volume of acid that's added that's less than 10, then we're in this excess OH region. Anything that's in that's greater than 10 is in the excess acid region. So it's a useful waypoint, and I often do this anyway. Any titration I do is sort of the first thing that I compute, because it gives me a framing for understanding where I am in volume space. So that I know if I think about additions of volume later, I know where in the curve am I? Am I before the inflection or past the inflection? And that dictates how I'm going to treat that mathematically or algebraically. So that's the first thing to do. So this alternative approach really is just thinking about the fraction of the distance that you've achieved up to the inflection point, or the equivalence point here. So if we know that this point is 10 and we've just added 3 of 10, then there are 7/10 of the excess hydroxide that are remaining in the solution, and that's the approach here that this is taking. So a little bit more intuitive in thinking about the titration curve. So you take the original VE, which was 10, so how many milliliters it took to get to equivalence, minus the 3 milliliters of acid that we're adding, which was the previous problem, over 10, which is, again, the volume to equivalence, and this gives us the 7/10, right? 10 minus 3 over 10. So it tells us what fraction of OH remaining in the solution before equivalence. That's what it's telling us. And then if we know what fraction is remaining, we're going to multiply that by what the concentration of it was to begin with, right? Because if we know what the concentration of the base was, but we know that we used up 3/10 of it, then we multiply by 7/10, and that'll tell us, you know, what concentration is left in the solution at that given point. We know that the original concentration of the base was 0.020 molar, so now we have 7/10 of that, those moles left over in the system. So let me write this out. So this is, I'll put hydroxide naught, meaning that's the initial concentration of the base before we've added anything. And then we need to compensate for the dilution factor, which is what is the how many moles of the base did we originally have, which we would then multiply by that volume, 50 mils, but we need to adjust that volume. So just thinking about this would be moles per liter multiplied by the volume, which would give us really the moles. 7/10 of the moles at this point is how much we have left in the system, but then we need to take those moles, the 7/10 of the moles, and divide it by the new volume, the adjusted volume. So that would be 50, our original, plus the 3, so 53 mils. And since this is mils over mils, that whole thing cancels, and that this is a fraction, so the whole thing, the units are still in units of molarity. So I'll just put this as the dilution factor. I'll say this is volume initial, V naught. This here is volume initial, V naught, and then this is volume added. So this is sort of the intuitive way to do this, as long as you have a general idea of where your inflection is, which is easy to do simply by just computing. You could do it M1V1, or you could just do this dimensionally and write it out as 1 mole of hydroxide required to react with 1 mole of H+. That give you the same result. So if you compute this, this gives you a hydroxide concentration of 0.0132 molar. So I'm going to use this method probably quite a bit in subsequent parts of this video and others to be consistent with your textbook. But know that either way, either of these approaches will get you to the right answer. I don't want to disrupt your intuition and tell you this is the way you have to do it. This is just adding on a little bit more flavor to how you might have thought about doing these types of titration computations in like a general chemistry course, which was more of a rote method. Now we're starting to think about this intuitively, so you can more quickly judge where you are in titration space rather than doing it out from first principles. So region 2 of the titration curve, strong base with a strong acid, we've already sort of alluded to right at the beginning of this video, but I'll walk you through it again. So I'm going to say this a million times, you're going to get annoyed with it, but whenever we're talking about equivalence points, and it's a little bit easier when we're talking about strong acid, strong base, but when we get to weak acid, weak base, I'm going to ask you over and over again, what do we have in solution at the moment we've reached the equivalence point? Not at the equilibrium, because that's the real question, but what do we have in solution before we've allowed it to proceed to equilibrium? The definition of the equivalence point is that we have added exactly enough H+ that it has canceled out or neutralized all of the base in solution. So what do you have if you only have strong acid and strong base in solution? Well, at that moment in time, right before equilibrium is allowed to proceed, you have pure water in the system because you added exactly enough protons to completely nullify all of the hydroxide in the system. So you have pure water. Then allow yourself, that tells you, okay, what equilibrium is important then, because this is all I have in solution, is pure water. Then you proceed to say, well, if I have pure water, what's it going to do if I allow it to proceed to equilibrium? Well, it's just going to do the opposite, right? It's going to then dissociate and trickle backwards a little bit. You force the equilibrium this direction because of the large 1 over K W. But then once it hits that point and you allow it to relax and re-achieve its own equilibrium, it has to satisfy its own equilibrium, which is always going to be H plus times hydroxide equals 10 to the minus 14. That has to be true if the system is at equilibrium. And if you allow it to proceed to equilibrium, then that means H plus has to be equal to 10 to the minus 7 molar at this point, which means the pH is 7. And so that's our equivalence point pH. That's how you would compute that. This methodology seems really obvious now, maybe for strong acid, strong base, but the same methodology is going to be employed when we get to weak acids and bases and diproducts, where it gets a little bit more complicated thinking about what do I have in solution and what equilibrium then should I employ. So in terms of volume, this is VE, and we talked about how to determine VE. There's sort of two different ways. You can either just do this dimensionally and say that, okay, I've got 0.0200 moles of OH per 1,000 mils. That's my original base concentration. Multiply that by the 50 mils. That gives me my base moles. Let me cross those out. So that's moles of base, and then I could say, well, 1 mole of base requires 1 mole of acid to react. We know that simply by the balanced chemical reaction here. So we can cross out then moles of hydroxide. That gives us moles of protons, and then the last step then would be to divide this by whatever the total volume of the system is at that point, using the concentration of our titrant, which was 0.1 molar. So we have 0.100 moles of H plus per 1,000 mils. So that crosses out there, and then we compute this to give us a VE of 10.00 mils in this case. That's sort of the brute force way. That will always work. The other way is just using M1V1 equals M2V2, which I showed you previously, where you have 0.0200 molar. You've got 50 mils of it. That's going to be equal to the concentration of your titrant and times X, which is VE. Solve for X, that gives you 10.00 mils as well. These two things are equivalent. They're equivalent processes. The M1V1 process will always work as long as the stoichiometry between your reactants is 1-to-1. And that's going to be true always for acids and bases because you're only thinking about them one step at a time. So this will always work for those. But if you try to apply the same logic to, say, a potentiometric titration, this might not be true, and then the M1V1 shortcut might not hold. So you have to think this through logically. If you're going to employ the M1V1, make sure that you're doing it for a 1-to-1. For acids and bases, it's always going to be cool. Or you can use sort of the brute force method, dimensional analysis, and I'll give you the right answer too. Okay, so region 3, the last region here, we know that we have excess protons because we're past equivalence, right? And the equivalence was defined as where the moles of acid equal the moles of base. Now we keep adding acid, and now we have excess acid or protons. So we need to compute the protons. We're going to do this using that fractional approach that I introduced in the previous step. So we've got our original concentration of our acid, which was 0.100 molar. And then we're going to multiply this by the fractional component. So we have our original volume, and I should add on here a specific example. So we're computing this at 10.5 milliliters of HBr added. We know that equivalence is at 10, so we're about a half a mil past the equivalence point. So the way we'll compute this then will be our whatever we add, 10.5, minus the volume at equivalence. That'll give us the excess, which is 0.5 mils. So that's what we would have done anyway. Divided by whatever our total volume is of the system. So 50 was the original plus the 10.5, which is what we've added. So what that's essentially doing is it's taking our original, I'll just write HBr naught. That's our original concentration of HBr, and it's multiplying by whatever the excess is here, which is 0.5 milliliters of HBr. times whatever that concentration is, which will give you the moles of HBr in excess, divided by the total volume of the system. So this is what you would do if you did this dimensionally. So either way is totally fine. This is just a fast way. So this would be our VE, this is our VAdd, and so collectively this group is VXS if you compute it. So it's the volume excess multiplied by concentration gives you moles of excess divided by the total volume. So if you do that, then the H plus concentration here is 8.26 times 10 to the minus 4 molar. So negative log of that gives us a pH of, let's see, that gives us 5.083 as our